Hi everyone, I'm Bertrand Leduc. I'm an assistant professor at Kyoto University and the co-founder of GeoLab. Today I'll be talking about the detection of methane emissions in multi-spectral satellite imagery using deep learning. This work has been done in collaboration with Claudia Herbert, who is at GeoLab. And thank you so much for the invitation. It's a huge honor to be giving this talk. So, let's see. So the overall goal of the project is basically to try to overcome some of the limitations of multispectral imaging using deep learning, and doing so to improve the detection limit of this data. I'll give a brief overview of methane. So everybody here is very familiar with it, but maybe later on, since on YouTube, it's useful to say just a few words. So methane is widely considered to be the fastest reducing methane emission. This is widely considered to be the fastest way that we have to slow down the global warming. And that is because methane is 80 times more potent in terms of greenhouse gas over the short term compared with the CO2. It lasts actually only about a decade in the atmosphere. And so it's the sort of the low-hanging fruit in terms of fighting climate change. And that explains a surge in regulations and emissions pledges around the globe. So that's sort of the good news. That is the low-hanging fruit. The bad news is that actually methane concentration keep rising, a few different reasons that I'll get into. And so those methane emissions, basically, they come for about a third from the oil and gas industry, about a third from enteric fermentation, so agriculture, cows in particular, and the rest mostly landfills and a few other sources. So that's the problem. And another problem, so although it's sort of a low-hanging fruit, especially since actually methane emissions tend to come from localized sources. That's also an advantage that makes it sort of a low-hanging fruit. But the problem is that actually it's very can be very difficult to find those point sources. They can come from quite a few different places, and existing methods basically fall in two broad categories. So sort of in situ sensors and sensors mounted on drones or car on planes, which have obviously very limited coverage and do not scale. You can also only do basically local surveys with those. And the other category, satellite imagery, that in principle should give us the ability to find all those sources. Actually, satellite-based approaches also suffer from some limitations, which I will get into now. So basically, satellites make a trade-off between four specifications. And the basic idea is that not all four can be good at the same time. You have to pick and choose a few of those specifications when you design a satellite. And those are the spatial resolution, the spectral resolution, the temporal resolution, and the coverage. And with those four specifications and the trade-offs in mind, there's two broad categories that make the trade-off on the spectral resolution. So the so-called hyperspectral satellites that have a very good spectral resolution, which allows for the precise detection and quantification of methane. And so given this choice of a very good spectral resolution, then the one has to pay the price with one of the other four specifications. And so, for example, there's so-called area mappers that pay the price in terms of spatial resolution. So the coverage is global. Again, the spectral resolution is very good. The temporal resolution can be good also, but the pixels are very large. That's the trade-off that's made. That's, for example, the Sentinel-5 mission with the TROPIUM instrument and the recently launched Methane Sat mission. And so those give very accurate idea of the levels of methane, but over large areas. So we don't actually know where exactly the methane is coming from. The other kind of hyperspectral satellites that exists are so-called task mode satellites. So that's, for example, the GHGSat constellation, the Prisma satellite, and those satellites pay the price in terms of coverage. And so they have good spatial resolution. Actually, the pixels can be pretty small, a couple, 10 or 20 or 30 meters. And the spectral resolution is very good, which then enables to accurately characterize methane. Temporal resolution is good also, but the coverage is very small. So the field of view, the swath of the satellite is small, which is basically the field of view of the satellite. And that means the satellite has to be tasked. So someone has to actually commandeer the satellite to look at a particular area. And that brings about the same kind of limitation that we were just talking about with the planes, for example, albeit at a larger scale. And now there's a second type of satellites which will be interested in this research, which is multi-spectral satellites. And so those make a completely different trade-off. The spatial resolution is good, the temporal resolution is good, it has global coverage. So interesting property in principle. We can look for methane at global scale and down to the point source, because the spatial resolution is good. The problem is that the price is paid in terms of spectral resolution, which means the signal, the methane signal, becomes very noisy. So the spectral resolution is not specific enough to accurately quantify methane. And via various signal processing, we can try to improve the methane signal to get at point sources. And so those multi-spectral satellites have the very nice property that have global coverage, good spatial resolution, good revisit times, but a low spectral resolution that brings about noisy data with respect to methane. And so detection threshold so far of about 2 tons per hour. And our research project has been to basically try to use deep learning to dramatically improve those signal processing techniques and to dramatically improve the signal-to-noise ratio in terms of methane signal and try to offset this weakness of multi-spectral satellite that is that the methane signal is noisy. And so I'll show you a bit and specifically what we've been doing, and I'll show you that actually using AI, we're able to improve by about an order of magnitude over the standard image processing techniques that are used to enhance methane, which actually almost entirely offsets, I would say, the limitations of multi-spectral satellite. I'll try to convince you of that. So now I'll talk a bit about deep learning in general and about basically this paradigm that we've been developing over the years. So if you're familiar with deep learning, you know that the crux of a deep learning project is data and lots of data, and also computing power, but mostly the bottleneck is data. So to train a good deep learning model, basically you need at the minimum hundreds of thousands of data points, preferably millions. We're dealing with methane detection in multi-spectral satellites. As I mentioned, the threshold so far is about 2 tons per hour. The data is very noisy, and so existing methane plumes in Sentinel-2 data basically have been labeled by hand, and there's only a handful of them. And so definitely not enough to train a deep learning model, in my opinion. And so we'll go a completely different route. And actually, it's an idea that we had a few years ago that we initially developed actually for Sentinel-1 data. So that's an interesting story, but basically, the idea is that there's a common problem that one encounters in remote sensing in general, but also in geophysics in general, which is that we are looking for actually a signal that's quite simple. So there's if we wanted to simulate or forward model the signal we're looking for, actually it's somewhat easy. But this signal that we're looking for, this simple signal, is buried in noise that has very complicated structure. So that's a problem that's very common actually in geophysics, and not just for methane. And so we started with this problem. We were looking for deformation signal in Sentinel-1 data. And actually, this signal was pretty simple to simulate, like elastic deformation. And it was also buried in noise, mostly atmospheric noise. And so the idea was to develop an AI paradigm where so the signal we're looking for is simple, and we basically hide it in this very complex noise that we can sample as many as we want. We can sample as much of this noise as we want. We can generate simple this simple signal as much as we want. And our idea is basically to hide the simple signals in these noise fields that we can sample as much as we want. So that's the overall idea. And now we applied this idea to methane, to looking for methane in multi-spectral data, because again we're in this framework where actually if one knows the methane concentration, it's trivial to predict the effect it will have on multi-spectral data, and so we can generate methane plumes with forward models that are more or less complex, but in general it's still quite easy. Then we can sample multispectral data as much as we want. So in particular here, we're working with Sentinel-2 data, so it's open source data. We have the entire planet every few days for the last almost 10 years. So we have as much data as we want. And we hide this methane with this methane signature in this complex noise that we actually sampled. So that's the overall idea. And doing so, we can generate actually very good data because this embedding of the methane, so it's quite physically accurate. So the details of the plumes, depending on the model, so we use Gaussian plumes, so very simple models. So the details of the physics of the plume itself are more or less accurate depending on the model, but the embedding in multispectral data is physically realistic. And we can sample real noise, real Sentinel-2 noise as much as we want. And so doing so, basically, we can generate very good training data in the millions and millions and millions. And doing so, we can actually properly train deep learning models. So that's what we did. In this version, in this first basically iteration that we published recently, we trained the model on 3.6 millions kilometers square. We crop those data in small subtiles. We hide the methane plume in it, and the deep learning models is tasked with finding where we hid it in the first place. That's the way we train it. So that's the figure from the paper that describes this paradigm applied to the search for methane in Sentinel-2 data. And that's one of the many architectures we trained on. And so before I talk about a few details of this architecture, I will say that actually the framework of the way we train our deep learning models actually is much more important than the details of the architecture. And I would say that for most deep learning projects that deal with scientific data, and especially something new, to a first order, the model is not that important, actually. The architecture of the model is not important. So that's something I think that's interesting to mention, and maybe is not talked about enough, is that basically the setup, the problem, and the training data brings about maybe 90% of the results, and the details of the architecture is for the remaining 10%, so like the last mile of the performance, which we are now very interested in, because so now that it's working well, we are focused on improving the last few percent of the performance, but yeah, that's something that actually is worth mentioning. So that's one of the best models, one of the best architectures we we have employed. So it's a unit. And a unit is basically a deep learning model that projects the data onto a much lower dimension space. So basically, it tries to compress the information, and that's when we are in this first portion of the model. So this portion of the model is basically trying to compress the information down to this much reduced space, and then it's so-called decodes it back to the initial resolution. And doing so, it's basically extracting the important information. So that's the idea of a unit architecture. So it's kind of the bread and butter of deep learning models. A novelty that we added is that we also use a transformer for the encoder part of the model. So encoders are somewhat new architectures that have been developed to deal with the issue of long-range information. So until recently, basically, deep learning models were all so-called convolutional neural networks. And then in 2017, Google published a paper about these transformers. So initially, it was for text, and now it turns out that it also works very well for images. And the goals of these models are to embed long-range information, because convolutional neural networks basically are a very local model. They apply local convolutions and are a bit myopic to the rest of the data when they're applied. And so transformers basically deal with this issue of understanding long-range interactions. And since we're looking for plumes that are propagating through the image, it makes sense that this kind of architecture that can recognize long-range interaction like that of a plume work well. Yeah. So now I'll talk a bit about the results, and I'll hurry a bit because time is flowing fast. So we have basically a few different ways we assess a model. First, we assess a model on test data, which is the standard way to evaluate deep learning models. So test data is a portion of the data set that we created that the model has never seen. So it's basically 25 to 50% of the data that we keep separate. The model has never seen it, has not been trained on it. This data is only used to assess the performance of the model on data it's never seen. There's a few ways to cut up the data in training and testing data. One of the harshest way to do it is to cut training and testing data in contiguous parts, which is what we did. So basically, the testing data is actually in regions that the model has never seen. So the tiles, the Sentinel-2 tiles used for training and the Sentinel tiles used for testing do not come from the same region. So it's a harsher test and a better way to evaluate how well the model generalizes to new data. It's really data it's never seen at all. And the plumes also, so those synthetic plumes are plumes it's never seen. And so basically here I want to show you that the model on those synthetic plumes embedded in real Sentinel-2 data, it's never seen, outperforms the classic multi-band multipass method, so invented by Varron. That so far was the state of the art to detect methane in multispectral data. So what we did is that we treat the multi-band multipass method as a classifier. So we have a threshold on the multi-band multipass method, and you see examples here. So here we hid a very, very strong methane plume in the data. So it's so strong that even by eye in band 12 without any processing, it's obvious. We applied Varron's method, the multi-band multipass method to it. And you can see in the background, so the RGB bands, but that's the classifier we get. This colored field. So that's one classifier we're comparing against. And we have our deep learning classifier, which it has been trained to try to find where we hid the methane plume. And on the last row, you see actually where we hid it. So the ground truth, it's been trained to reproduce. So for very strong plumes, you can see that the multi-band multi-pass method and our deep learning model have very similar outputs. So it does map out where we hit the plume. And now what's interesting is that we're gonna lower the signal to noise ratio. So we're gonna decrease the methane concentration of the plumes we hide, and we're gonna look at scenes that are more complex with respect to basically the multi-band multi-pass output. And so we look here. So here we're at a signal to noise ratio pretty close to 1. And so we're going down to a signal to noise ratio of a few tens of percent. Already, if we apply the multi-band, so in band 12, it's lost. Already, we can't really see where it was. Even in the multi-band multi-pass method, already it's a bit hard to find by eye where it was. The learning model has no problem. And now let's skip to actually low signal to noise ratios. And very complex scenes. So for example, vegetated scenes, this kind of scenes where the plume is very small. We applied the multi-band multi-pass method. By eye, at least me, I could not say where the plume is in either of those two scenes. The deep learning model still succeeds, and that's at signal to noise ratios of a few percent. If we statistically assess our model, we find that it basically fails below 10% signal to noise ratio, whereas the multi-band multi-pass method basically fails between signal to noise ratio of 1, starts to fail. And so we see here already on those Sentinel-2 data where we hit the plume, it's 1 order of magnitude improvement. Now for the rest of the talk, I'm only going to talk about now real plumes. So we have our models now they've been trained. We're happy with them. We evaluated them on those as I just showed, and we're gonna apply them. To starting with here control release experiments that were conducted in Arizona. And that are summarized in this paper actually, so it's the Stanford group organizing those control releases. Those are large plumes, so especially these ones, so 7 tons, 5 tons, they're very large plumes. The signal to noise ratio is very good. Actually, I should have put it here, but it's in the region of performance where even the MBMP would work well. The deep learning model has no problem, which is expected, but reassuring. Now we start looking at plumes in the ton. So this one is 1400 kilos per hour. Basically, 1 to 2 ton is the limit of the multi-band multi-pass in general in semi-arid areas like Arizona, with the human looking at the multi-band multi-pass. So it's basically like when one says the limit of detection of methane in multi-spectral satellite data is, it's basically the MBMP method to increase, to enhance the methane signal, then someone looking at it and doing so, the limit is basically 1 to 2 tons. So we're reaching the limit of the MBMP method. And here we're looking at a few other ones. So a different campaign, again, organized by Stanford in Arizona also, but a different location, and smaller releases so that we're timed with the Sentinel-2 satellite. Again, around the limit of the MBMP method. And so here you're looking at just the output of the deep learning model. So we feed it the Sentinel-2 data in the same way that it's been trained. And here you see the full output of the model. So here, basically, that we see that basically at least it is completely automatizing what a human would be able to do with Sentinel-2 data. And I'll just show a last example of control releases. So this one is interesting. So just like a null test on the left. So a day where there were no releases. So interesting to look at the output of the deep learning model. It is indeed finding no methane. And then another day, so we're looking at the data. It's interesting. We thought we maybe had a false positive because we have detection on a day where there were no releases timed with Sentinel-2. But weirdly, it was exactly where the release takes place, because so something I should have mentioned, the deep learning model is trained with no a priori on the location of the source. So there's a few different ways to do it, but basically this model is trained with the source that could be anywhere in the image. So it's a strange coincidence to have detection exactly where the release experiment is. And actually it's because there was a release time with Landsat 8 just a few minutes prior. And so although the experiment is interrupted, we can still see the plume that was timed with Landsat 8. So that was a fun thing to see. So since the limit of what could be done so far in Sentinel-2 data is 1 to 2 tons per hour, actually, so far there were no control release experiments that we could use to assess our model below 1 ton. But fortunately, actually, this year, the Stanford group will organize Sentinel-2 timed releases below 1 ton per hour. So we're very excited to participate in that. Be very interesting. So now, since there's no control release below 1 ton per hour, we have to find a different way to assess what the limit of our method is. And the way we try to do that is by comparing our method with airborne detections. So airborne detections go well below 1 ton per hour, especially in some arid areas like the Permian. We have very small for our purposes detections. And so here I'm summarizing our results from comparing our detections with 5,000 detections from Carbon Mapper. So Carbon Mapper has a data portal that has all the detections of the GAO and Averys NG missions, and we took all the detections that were on the portal in the Permian. So it's a bit different than in the paper, but it's basically our latest results on this data set. So we have 5,000 airborne detections. We take Sentinel-2 data in the 2 weeks preceding the airborne detection, and we report if our deep learning model is able to detect, has some detection in those 2 weeks leading up to the airborne detection. And we plot that as a function of the emission rate reported by Carbon Mapper. So that's what you're seeing here. And so it's bins of 500 of those airborne detections and the fraction of our detection. So that's what it looks like. So basically, there's a plateau above 200 kilos per hour, and then it precipitously drops below 200 kilos per hour. And this plateau coincides with the persistence actually in the catalog. So at least it's the persistence in a subset of the catalog, should I say, that's reported in this paper by Cuthworth. And so we argue that these results is a good indication that indeed, as we found on the synthetic probes hidden in real data, as we found there, we also find here a roughly 1 order of magnitude improvement in our detection capability as we go from about 2 tons per hour down to 200 kilos per hour in terms of reliable detection limit. This improvement from 2 tons to 200 per hour. So there's so here you're looking at the distribution of the size of the emissions in terms of cumulative fraction of volume. So basically, the sources above 1 ton per hour account for about 25–30% of the emitted volume, etc., etc. And so by going from 2 tons to 200 kilos per hour, we basically go from the ability to detect about 10% of the emitted volume all the way up to about 80%. So those distributions are from a paper by Jacobs in 2022 for the Permian. So we're talking about the Permian. So here I'm just showing a few examples. For the rest of the talk, I'll go faster. Basically, I'll just show a few examples that are interesting. So here's a figure from the paper where we're analyzing a subset of the catalog. So the figure I just showed is a larger catalog of 5,000 plumes. In the paper, we're looking at 2,000 plumes in the US. And here you're looking at detections of our deep learning model in those few days leading up to the airborne detection. So a few examples from a variety of scenes and a variety of source types, mostly oil and gas, but there's also coal and actually also agriculture as images. And so also I mentioned that 200 kilos per hour seems to be a reliable detection limit, but we see quite a few actually sources that were below this threshold. For example, this tiny. And here we're zooming in actually on one of those tiny sources that we're able to detect. So at 60 kilos per hour, we don't detect all of them, but we do detect quite a few of them. And I'm comparing with the multi-band multipass, so it gives you an idea of this kind of small sources, even in a semi-arid scene, the signal-to-noise ratio is not great, definitely well below 1. So if you didn't know the potential sources here, as a human looking at this scene, there's no way to say that's an emission, that's not, etc. A deep learning model manages to do that. So not only does it automatize the job of a human looking at the BMP output, but it also improves on it by about 1 order of magnitude, as we saw. So I'll talk a bit about our latest developments, basically over the paper. So there's going to be less figures. But so, as I mentioned, so the details of the architecture is basically the last mile in any deep learning project. But now that's where we are. So we're developing all kinds of architecture that are improving the performance and training them on much larger data sets. So we're iterating on that. So we have a data set actually that's 100 times larger than the one we trained on initially in the paper. And we actually have developed a cloud implementation. And so the idea, I'll talk a bit more later about it, will be to have something a bit like the carbon mapper data portal actually with our detections, because really the power of Sentinel-2 and the automation we developed, I think, is that now we will be able to deploy at very large scales and the detection down to the point source level, and also in time. So we potentially have almost 10 years of data to analyze, which would be impossible to do by hand, of course. So that's an example of our early large-scale campaigns that we're doing. So here we're looking at, we've basically looked at the county level. So here in New Mexico, in the Permian. For this county, we look at the every Sentinel-2 data that we have. Using the same approach as you saw so far, we find about 3,500 detections. If we extrapolate to the whole Permian in terms of number of wells, so if we look at how many wells we're looking at versus how many wells there are in the whole Permian, we're expecting more than 100,000 detections a year once we start deploying our approach on the entire Permian. And that's just from Sentinel-2 data. There's also Landsat 8. That's basically the same kind of data. Now I'll just zoom in on a couple of examples just to show you. I should have put the source rate. Sorry about that. I forgot to do that. So in the background, you see the high resolution optical imagery. And here you see the output of a deep learning model that tells us there is methane there. And that just shows you that we are able to say where the leak is coming from. And in some cases, when the potential source is quite isolated, so here we can see there's a flare stack, and actually like, there's nothing else that could leak other than this flare stack. And so from Sentinel-2 data, we're able to say it's this flare that was not lit properly or not lit at all. And now we can do that everywhere automatically. So we're starting to do that, this kind of large scale studies. And so I thought I would just mention, so there was recently a very interesting paper by Varon, where he looked in tropomy, what does methane emissions correlate with, if it correlates with anything. So it's at the tropomy scale, so at the basin level, it seems to correlate basically with drop in prices or with increases in new wells. And so it's very interesting because actually in our initial studies, as you just saw, so systematically looking at large areas in the Permian, one thing that is quite striking is that when there is a new well, there's usually strong emissions associated with it. So that's something very interesting that we're currently investigating, and that is correlated by this research by Varro. So another nice property of Sentinel-2 is that it's not just in the Permian. So I've been basically only talking about the Permian so far, but Sentinel-2 data is collected everywhere. As I mentioned in our initial studies, there were other kinds of sources than oil and gas. And so we can actually look at any kind of methane source anywhere in the world. So here I'm showing a few results in collaboration with Giannis Binitoglou, where we looked at a few different sites of interest. And so I'm showing you here a few of our detections. So there's a landfill in Mozambique, where we see basically continuous emission. And whenever we have Sentinel-2 data, there's emission. So super interesting. A landfill in Spain, where we seem to see multiple sources actually, and mines in India, coal mines in India. So basically, that shows you that we have basically potentially a tool to look for methane emissions of all kinds globally over years and automatically. And it's really like within reach. So it's within reach, and we're starting to work on that. So as I mentioned, we're training our models on very large data sets. So the last mile, those last few percent that do depend on the architecture and the size of the training set. We actually recently started the training on this very large training set. It will take about 3 months, and so it should improve quite a bit. We hope the detection threshold and our false positive rate, which is critical and directly interlaced with the detection threshold. Our plan is to apply the model starting with regions of interest. So basically oil and gas basins and landfills in the US first since 2016, and then progressively add regions. In parallel to that, we will apply our model to Landsat data, Landsat 8 data. So the data is very similar, so it will barely take any retraining, if at all. Something else that we have planned is to actually look at ghost data. So I'm sure everybody saw the really great paper by Marc-Watin Guyou and PNS that got out, where he shows that ghosts can be used to basically look in real time at very large leaks. So we're talking about leaks above 50 to 100 tons per hour when one uses the MBMP method and GOES. The GOES data is actually somewhat similar to Sentinel-2 data in terms of spectral resolution, but the pixels are huge. And so we think that we can apply the method and hopefully get a similar improvement. So if we can improve GOES by an order of magnitude, then we'll be able to image in real time leaks down to 10, 20 tons per hour, which would be very interesting too. And we will start looking at hyperspectral satellites as well. it will be interesting to see if deep learning can bring about the same kind of improvement there as well. TBD. So as I mentioned, we are planning to have a platform a bit like a carbon mapper with our point source detections in multi-spectral data. I'd be thrilled if some of you want to participate in the beta that we plan to have. And our idea is that the platform will be free for academic research. And so, yeah, let us know if you're interested. If you have interesting data sets, if you know of data set that could help us test the method more, we're also super interested. And we're also looking for a consortium to join for the recent grants. So the methane emission reduction program just put out 3 weeks ago very large grants, and they're so large that basically it has to be replied as a consortium, and so we're looking for a consortium to join. So if you know of a group, or if you are a group applying to those grants and you'd be interested in collaborating, would be thrilled to talk. So to conclude, basically through software development, we managed to offset the limitation of multi-spectral satellite data, which is the bad signal-to-noise ratio of methane signal. And so doing that, basically, we bring about a method that approaches the detection limit of 5 spectral satellites, but doesn't suffer from its limitations in terms of coverage or spatial resolution. That's summarized in this nice plot that I stole from Varron's presentation at the Meta seminars a few months ago. So it's basically the range of operations of the different methods. So here you have the global area mapper, so like TROPOME and MethaneSat. Here you have the hyperspectral target mode sensors like JGSat and Prisma. Sentinel-2 and Landsat are sort of in between, and now with AI, we're managing to also approach the detection threshold of those hyperspectral target mode satellites. And so thanks a lot for listening to my talk. I hope it was interesting, and thank you so much for the invitation. It was a huge honor to talk at the Meta seminars. So this one has been in collaboration with Claudia Hulbert at GeoLab, and we'd like to acknowledge funding. So this research has been funded by an SBIR grant. So I think it's uncommon that research is funded by SBIR. So interesting to mention, and we're very grateful. And I'm also supported by a Hakubi fellowship from the GSPS, the Japanese Society for the Promotion of Science. Thank you so much.